So the plan for today is the Bethe Ansatz. It's going to be a bit heavy, but I'm sorry for that. You have to go through it once in your life. It's like the Jacobian for random matrices. But before that, I will finish what I said yesterday about this matrix ansatz and these numbers that seem to have puzzled you a lot. I don't want to enter too much into the details, maybe during the exercise lessons and so on. But the idea was that these people, Derrida and collaborators, tried to solve the TASEC, the totally asymmetric exclusion process, with all rates equal to 1. Again, a particle can jump only if the site next to it, because it's totally asymmetric, is empty. You may have many particles in the system. There are 2 to the power L configurations. And what they did, they explored the system. So they tried to solve systems of size 1, 2, 3, up to 8 or 10. So for 10, you have 1025 numbers to look at. Because here all the rates are equal to 1, you will get fractions. The probabilities are given by rational numbers. And they observed that these rational numbers have, so this is a numerator over denominator, and they observed that the denominators are given by a simple series. 2, 5, 14, 42, 100, 132, 429, and so on. And this series is a famous series known as Catalan numbers. So the denominators were given by these Catalan numbers that you may or may not be familiar with. So 132. And these numbers count for trees. So maybe during the tutorial, exercise session, we shall count the number of binary trees. It's a simple exercise in combinatorics, but again, it's an exercise one needs to know how to do. Then they just wrote the numerators, and for example, for 2 sides, they found that the numerators are given by these numbers. So remember, you have to divide everything by 5 so that it adds up to 1. And they made some observations. I mean, physics is an experimental science. They made the observation that if you iterate that and do then 3 sides and 4 sides and so on, they observed that if you take anything, any pattern, and you put zeros to the left, you have the same numerator, the same integer. So if I take any pattern x, x is a pattern, is a configuration with zeros and ones. So the weight, I will call this the weight, without the denominator. Because the denominator, we know what it is, Catalan. If you don't know, just Google it. You will see that if you Google 2, 5, 14, 42, immediately it will tell you Catalan. And there are also many sites now, this Conway and Sloan site of integers. There are plenty of ways of guessing numbers, if you don't guess them. And they notice that the weight of, you add a 0 to the left, it's the same weight. It doesn't change the weight. It's invariant. So if I take any pattern, I don't know, 1, 1, 0, 1, it has the same weight as 0, 1, 1, 0, 1, and as 0, 0, 1, 1, 0, 1. And they also noticed that the weight of x1 is the same as the weight of x. Again, for this very special problem with these rates, if I change the rates, it will change a bit. And finally, this is not enough to compute everything. They notice something more subtle, but which is very nice and very important. If I take any configuration, let's take any configuration, for example, this one, a 4-side configuration, they notice that the weight of this thing, so let's write it here, the weight of 1101, so it's given by, I don't remember, 1101 is given by 3, in fact. And they notice that the 1, 0 here, you can break it. The idea is to break a configuration into smaller ones, and they notice the following recursion relation, that it's equal to the weight of 1, 1, 1, plus the weight of 1, 0, 1. Okay, this is a special case. But they looked at many, many cases, and then they noticed a very general rule that if you have anything followed by 1, 0, followed by anything, so this is any pattern made of 0 and 1s, this is any pattern made of 0 and 1s, and you have a 1, 0 somewhere, then the weight is equal to the weight of x1y plus the weight of x0y. It's an observation. For example, here it's a special case, x is 1, y is 1, and this is true. But I could have taken anything, I don't know, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, and broken this one. Or I can break this one also. Or I can break this one. If I have a 1, 0 anywhere, I can just break it into 1 or 0, and then sum the weights. And then they notice that these rules are enough to calculate all the weights. If you think about it, now you have enough information. Again, it's empirical. There is no mathematical proof yet, but you have enough information to determine all the stationary weights. So that's what happened with the help of the computer and so on. And then all this, you can put it in a very formal way. So they invented what is now known, there are many names, but it's called the matrix Ansatz. I'm not sure they chose this name. Sometimes you call it the matrix representation method, or whatever you like. But the word Ansatz is, of course, chosen in memory or kind of metaphor for Bethe Ansatz, which I'm going to teach you later. And indeed, this method has some relation with the Bethe Ansatz, which are not completely clear. It's still an open problem. I will teach you that. I will teach you the Bethe Ansatz. You will see that there are some common features. Yeah. Well, if you wish, yeah, but yeah, partly. So I'll teach the coordinate Bethe Ansatz today, but the relation between the two techniques are not completely known. The advantage of this technique is that it's much simpler than the Bethe Ansatz. So this has become a method which is quite widely used for one-dimensional non-equilibrium problems. It's not a general method, but it's much more general than what they expected it to be at the beginning. And if you want to learn much about that, there is a nice review paper by Richard Blight and Martin Evans in JPhys. I don't know, 2, 3, 4 years ago, 2008 or 7 or 9. I don't know exactly the year. It's called the User's Guide to the Matrix Representation Method. I mean, just Google it, you will find it. Okay, so now I don't want to spend too much time on that, but I want to tell you about the matrix Ansatz. So this was the recipe to find it, but of course it's not written like that in the papers. All this is hidden. And what is given in the papers is the solution. 2 to the power n configurations. Of course, a configuration is just a binary number. For example, this configuration is just a binary number 0, 1, 1, 0, 0, empty, occupied, occupied, empty, empty, empty. Okay? And the idea is that if you have a configuration C like that, okay, it sounds bizarre, but well, the idea is to replace the zeros by an operator E. So it's purely formal. Think about it like a computer, a program, if you wish. So 0, we write it as an operator. And 1, we write it as another operator. So instead of representing the configuration 0, 1, 1, 0, 0, we can write it equivalently. It's just a change of notation as E. dd is d square, E cube, which is the same way of writing it. So you just translate things. And the matrix Ansatz is just that the stationary weight of a configuration, let's say this one, but it could be any other one, is given by, of course, always you have to normalize. And even if this z is not a partition function, people like to use z as a normalization. Satya used the same letter before. And it's, so consider now E and D as operators. So this is a kind of matrix. And you have to calculate a matrix element of these operators to get the weight. So the idea is that there exists a bra and a cat. You're all familiar with bra and cats, yeah? You did quantum mechanics. And if you evaluate this matrix product into this bra and cat, so again, E, well, D, D, E, E, E. This should give you the right weight. Of course, for the moment being, it's empty because I didn't tell you what D is, what E is, what W is, and what V is. But if in a second, I will give you precise information about these three things. So if I tell you what these objects are, or how they act on each other, this will give you the weights. Is it clear for everybody? So now, of course, this is not arbitrary. You have to choose the algebra, you have to choose D and E. And the key point is that D and E, the operators D and E, must satisfy a quadratic algebra. So D times E must be equal to D plus E. V is an eigenvector of D with eigenvalue 1 over beta, where beta is the exit rate. And can you read here? W is an eigenvector of E with eigenvalue 1 over alpha. So this is the algebra. And the idea is that having this algebra, you can simplify any word. So this is maybe slightly long to simplify. I will take a simpler example, just 3 sides. If I have to compute that, how will I do? Well, E times W is 1 over alpha W. So I can kill this one. Okay. DE is equal to D plus E. So okay, dV is 1 over beta V, so I use it. EW is 1 over alpha W, and the only thing which remains in the end is this scalar product, which will be an overall factor. So I know that the weight of this configuration, the stationary weight of the configuration 1, 0, 1, 0, is proportional to, this is not an alpha, it's proportional to this number. Is it clear for everybody? So now you should be able to connect it with the numerical observation that we did before, following Derrida et al. If alpha and beta are equal, it means that this is 1 and this is 1. So this means that putting e's to the left or zeros to the left does not change anything. Putting d's to the right, if beta is 1, just leaves v invariant. So it does not change anything. So it means that you can just remove the e's to the left by putting 1 over alphas, or 1 in the case alpha equal to 1, and remove the d's to the right if there are any by just cancelling them with v. And the famous relation 1, 0 is equal to 1 plus 0 is just this algebra here. So alpha and betas are the exit and entry rate here. They are related to the problem here. A particle can enter into the first site with rate alpha. So if the first site is empty, a particle can be put there with probability alpha dt during time t and t plus dt. And if the last site is occupied, the last particle can be ejected with probability beta dt between time t and t plus dt. So this is the thing with Ansatz. I mean, this is what works. So you can say that they looked at special cases, they understood how the combinatorics works, and the algebra here just encodes the combinatorics. Now, your question is very important because I forgot to say something very important, but probably Abhishek and Sanjib told you about it already. We want to find the stationary weight, the stationary measure of each configuration. And it's a Markov process. And it's a Markov process which has the property of being non-reducible. It means that from any configuration you can go to any other one. There is no subgroup of configurations which don't talk to the others. If you start with any configuration, you can just reach any other one. I mean, from any configuration you can reach the empty configuration by pulling all the particles out, and then you can build up any other configuration. And these kind of Markov processes have, oops, maybe I will move that. I cannot go much below. Will you mind if I open one of my buttons? No, you can't see it, it's okay. I will remain decent, don't worry. This thing? So it's a bra and ket, it's just a scalar product, but this will be an overall constant that will not change anything. Okay, so one very important point is this Perron-Frobenius theorem. Did you tell them about it? Yeah, Abhishek? This Perron-Frobenius theorem tells you that for well-behaved Markov processes, and the AZEP is one of these, the stationary state is unique. There is only one. Okay? So you can do whatever you wish to find it, even things which are totally not moral. If you find it, you find it. Okay? So the thing is that this gives you the result. It works. And then, of course, probably I will not do it now because I really want to go into the Bethe Ansatz. I was hired for the Bethe Ansatz, not for the matrix Ansatz. But you can prove that this gives you the stationary state. You can prove that if you calculate the weights according to this algebra, it is a zero vector, a right zero vector of the Markov matrix. And because of uniticity due to Perron-Frobenius, it's the right one. So you understand the trick. Because you look for something which is unique, if you find it, you find it. But then, of course, finding it requires some guessing, some tricks, and so on. Okay, what else do I want to say? So with this algebra, you can calculate things. What can you calculate? You can calculate the current, for example. A particle here, site I, empty at site I plus 1, rate 1, and something before. So what is the current, for example, between site I and I plus 1, J between I and I plus 1? So we are exactly in the situation that, for example, Satya described an hour ago. We know the measure, so we know the P of lambda 1, lambda n, and now we have to compute observables. So we have to make some sums, some calculations. So what is the current between I and I plus 1? Well, it is the number of configurations with I occupied and I plus 1 empty. These are the ones which will give you a unit current between time t and t plus dt and contribute to this current per unit time. The other ones are useless. Okay? If both sides are empty, you cannot create a current between I and I plus 1. If both are occupied the same, and because this is TAZEP, I just jump towards the right. If this one is empty and this one is occupied, I will not create a current in this bond. So the current between I and I plus 1, the stationary current, it is the sum of the weights of configurations having I occupied and I plus 1 empty. Okay? So if I use this matrix Ansatz, it is 1 over Z, because the normalization is always there, the sum over all configurations. So what does this configuration look like? I can put anything on the first side, D or E, anything on the second, but on the ith side, I'm obliged to put a D, and on the I plus 1 side, I'm obliged to put a E, and here I put anything. Do you agree with that? Yes? So here it can be D or E, 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 and I have to sum over all such configurations. I'm not going to rewrite that, okay? So see accordingly, or I don't know what to say, but all the correct configurations. Sorry? Because I'm summing over all configurations such as the ith site is occupied and the I plus 1 site is empty. So I have to have a 1 here and a 0 here, and I can have whatever I wish elsewhere. So W and V's are vectors, bra and ket, like in quantum mechanics, and they are just defined to be V is a right eigenvector of D with eigenvalue 1 over beta, and W is a left eigenvector of E with eigenvalue 1 over alpha. Do you agree that this will give this? L moins 1 moins I V. Do you agree with that? It's a L here, yeah. Because if you now expand D plus E to any power, this will generate all possible patterns of length I minus 1. And if you expand D plus E to this power, L minus I minus 1, it will generate all possible patterns here. But of course, here it's fixed. Okay? And now look at the nice thing. D plus E is equal to DE. So usually we call it C. We just define C because it's easier. And this thing, you can rewrite it 1 over Z W. So this is C, this is C, this is C. C to the power L minus 1 V. L minus, because I want all this to be L. So this can be anything, but this is fixed. No, because, no, look, I mean, I want to construct something which is of length L. So how many sides do I have remaining here? I always make this mistake, but I think it's L minus I minus 1. You know, you have to count how many, these kind of problems which are horrible. I mean, how many sticks you have and how many meters you have. But I think it's L minus 1 minus I. If there is no minus 1, correct it. But it's not important. Yes. is the sum over all C of W anything V, all possible patterns, and all possible patterns, you generate them like that. So Z is given by W C to the power L V. Do you agree with that? If you don't, well, you should. And if you don't, well, again, try again on small patterns. For example, if you take a system with two sides, you have to add DD plus DE plus ED plus EE, and this is D plus E square. Don't forget, D and E do not commute. Okay, so DE and ED are not the same. So this gives the nice final answer for the current in the stationary state. And the current is just given by this ratio. And as you see, it's completely independent from the site I, and this is normal because there is no creation or destruction of particles in the bulk of the system, so the stationary current should be the same whatever bound I plus 1 I look at. It's the same everywhere, and this shows you that. Okay, so you believe now that this kind of thing will allow you to calculate any correlation, but this is purely formal. I mean, you see, okay, I mean, what is C, what is D, and so on. The nice thing is that these matrices, you can represent them as concrete objects, or you can play with the algebra like that, and you can get formulas for the current, and formulas for correlations, and formula for Z. For example, there is a nice formula for Z, and so this, I think I will leave it for, again for the, everything is left for the exercise sessions, so that's a good, but again, I want to do something more substantial today, but you can get an explicit formula for all these things. So I just write it here. Just to tell you that this is not purely formal. You can get numbers in the end and formulas. I mean, you don't have to write it. I mean, but there are concrete formulas which allow you to compute the current, to compute correlations, and things like that. And in the end, playing with this algebra, you can get a phase diagram of the system. So I will remove that. You can get a precise phase diagram of the system in function of alpha and beta. When L goes to infinity, the system can exist in 3 phases. Usually you put the alpha here, the beta here. Usually alpha and beta are normalized to be less than 1. One half, 1/2. Okay, this should be the diagonal. So you have 3 phases. You can guess what they are. For example, here, beta is small and alpha is big. It means that you can put particles easily but not extract them easily. So this is called the high density phase. High density phase. This is called the low density phase. And thanks to the formulas there, plus the formula I just wrote and erased, you can calculate the asymptotic value of the current. So for example, here it's given by beta 1 minus beta. Here it's given by alpha 1 minus alpha. You can also calculate the bulk density. The system in the bulk has a, so the density in the system has some boundary effects but in the bulk there is a density which is more or less constant. So there is a bulk density. Okay. So of course in the high density phase, the bulk density is going to be high. I hope I didn't make a mistake. I always confuse between low and high density. If you allow me, I will just check. Will be given by 1 minus beta. Here the bulk density will be given by alpha. And in this phase, what happens in the bulk does not depend on alpha and beta anymore. In fact, it's called the maximal current phase. So J is given by 1/4 and rho is given by 1/2. And on this line something special happens. It's called the shock line, and we are probably not going to talk about it more than that. So thanks to this exact solution, of course you can obtain it by other means. You can obtain it by mean field if you like, but you are never sure of what you get by using mean field. This is an exact solution, and you get the phase diagram of the exclusion process completely with the different phases and the behavior in the different phases. You can calculate correlation lengths like the ones we saw yesterday with Schumit. If you take two sites and you want to see how the correlation between two sites behaves, there is a correlation length psi, at least in these two phases, low density and high density phases. You can calculate it using the matrix Ansatz, and so on and so on. So again, I mean, this is a kind of strange method, but it has quite a lot of applicability, and in particular, it can be generalized to the partially can solve the general case. The general case will be where particles can jump in both directions and can enter and leave from both reservoirs. So you will have 4 rates. You will have a rate alpha, beta, gamma, and delta. And you have to modify these relations by using alpha, beta, gamma, delta. I think it's not useful to enter into the details. There is a nice algebra, and using that nice algebra, you can generalize to the phase diagram of the general model and obtain exact results. Okay. Do you have any questions on that? But of course, we know nothing about the evolution of the system. We only know what happens if you wait an infinite amount of time or long enough time, how the system behaves when it's stationary. But we would like to know how the stationary state is reached. So to understand how the stationary state is reached and how the time-dependent properties of the model look like, we need to know the eigenstates and the eigenvalues of the Markov operator, of the Markov matrix. We need to know the transient behavior of this operator. And this transient behavior will be reached only if we are able to diagonalize this Markov operator. You agree with that? Just like the Hamiltonian, this stationary state is the same as the ground state, if you wish. And we now need to know excited states to know the dynamics. And the matrix Ansatz is not able to answer that question. This question will be answered only by the Bethe Ansatz. So I think it's time now to go to the Bethe Ansatz, which is a much more general and older method. And this Bethe Ansatz has different forms, more and more elaborate. And the form we are going to talk about today is the so-called coordinate Bethe Ansatz. Not for solving the exclusion process, unfortunately, but to solve the Heisenberg spin chain, which was a model for quantum magnetism. Okay? So he invented it in 1931 in the context of quantum mechanics, the beginning of quantum mechanics. And since then, this technique has become a chapter in physics, in theoretical physics. It has become a subdomain which is known as the domain of integrable systems. So it's a huge subject, an enormous subject with books, with 10 or hundreds of people working on it. And okay, so of course I'm going only to scratch the surface. So you see 31, so 6-7 years ago it was 75 years of the Bethe Ansatz, and there were many conferences and so on. And I just, in fact it's my collaborator Tridip Sadhu who found in Physics Today a small feature article by Bachelor about the story of Bethe Ansatz, and even a photo of Hans Bethe and so on. So I could not copy hundreds of them. Well, yeah, maybe even better, I just copy 2 or 3. I will leave them here, and then you can look at them, find them on the web, and so on. So it's a nice history article on the Bethe Ansatz. And just to trace the history in a few words, so what can we say about the history? So Ansatz is a German word which means trial, beginning, or trick. So he just used it as a trick and never come back to it again, and slowly developed into a whole field. And some landmarks are Lieb and Lininger in 63. They solved the delta Bose gas. So the Bose gas with delta interaction. So this was a purely mathematical problem in quantum mechanics. So the Schrödinger equation, the n-body Schrödinger equation with delta interactions, a delta potential. So this was a purely mathematical problem at that time. It has become an experimental tool and problem now because people study cold atoms. Then the people who worked on it, I don't know all the dates by heart. Of course, there is a famous contribution by Young, C.N. Young, who generalized the solution of Lieb and Lininger in 67. They studied the Bose gas. He studied more complicated gases with some spin degrees of freedom. So this was more the quantum mechanical world. Then in the 70s, there was the studies of these 6-vertex and 8-vertex models. I'm going to tell you about these models in the 4th or 5th lecture. They are generalizations of the Ising model, and the exact solutions were found, some exact solutions were found by Baxter in the 70s, I think, yeah. And also, of course, again by Lieb and Young, the same people. And they developed a whole engineering to use this method. And so this is the exact solutions of this generalization of Onsager solution of the Ising model. And they developed a whole algebraic tool which culminated into the so-called Young-Baxter equation. That we may scratch on later. I'm not sure, it depends on the time and on how it goes. And then by the end of the 70s and 80s, the Russian school, the Leningrad school, Fadeyev and many other people, Kreshetikin, Sklianin, Kulish, and so on, took over. Sorry? Yeah, no, there are many names. Yeah, we Korepin, and yeah, if I start, first of all, my Russian is very bad, and but usually, sometimes you just give the name of the founding father or the kind of charismatic figure. So Fadeyev is probably the head of the school, but many people did that. And from the mathematical side, there is a very big mathematician called Drinfeld. He won the field medals. And they really turned it into another chapter of mathematics, which is called the algebraic Bethe Ansatz and quantum groups. I'm just throwing names and words just to give you a kind of idea of the galaxy around this Bethe Ansatz. And this really became the subject of integrable systems. And just to tell you, I mean, this is a tool, this Bethe Ansatz. So Bethe again never came back to it. Huh? He lived almost 100 years. He died a few years ago, but he almost didn't follow and didn't know that this became a whole chapter in theoretical physics and in algebra. Quantum groups are really a chapter in mathematics. And it's a very important tool, so in mathematics, algebra, combinatorics, but we are physicists, so it has been used heavily in solid-state physics. People like Nathan Andrei, Wigman, Svelik, they solved the Kondo model with it. The Kondo model that was first solved by Kenneth Wilson using renormalization by an approximate method, by this coarse graining and rescaling method that Schmidt is teaching us. It was solved later exactly this model of Kondo by Bethe Ansatz by some Russian-Israeli people. It's also used for the Hubbard model, of course for spin chains, as it began with. For quantum entanglement, now people are turning it into a numerical and computational tool to solve exactly finite spin chains. And very bizarrely, and this I cannot tell you anything about it, but Schmidt can, it has become very, very fashionable in the last 5–10 years in string theory. Okay, I just cannot tell you why, but there's a huge number of string theorists who claim that they have discovered the Bethe Ansatz and now work on it very, very deeply and using very complicated methods. But all in all, this is the same Bethe Ansatz. Just before finishing this historical review, there is a nice quotation by Feynman. So Feynman died in '88, and just a few months before dying, he became interested in this Bethe Ansatz. And so in this small feature article, they quote him. So Feynman says in '88, it's maybe his last paper is about the Bethe Ansatz. So he says, I got really fascinated by these 1+1 dimensional models that are solved by the Bethe Ansatz, and how mysteriously they jump out at you, and you work, and you don't know why it works. So I'm trying to understand all this better. So this is one of the last quotations of Feynman. And again, you can ask Schmidt, because he was a postdoc with Feynman during the last years of the life of Feynman. So he saw Feynman working on the Bethe Ansatz, and he has many anecdotes. So if you want to know more, ask him, because he was there. I wasn't there yet. I regret it. One of my dreams was to see Feynman, but he died at 70. He could almost have been alive now, but it's too late. Okay, so that's the end of the historical, and now we shall enter the details. So the Bethe Ansatz is a method. It's a technique for solving problems. It doesn't work always. It works rarely. But when it works, it's a miracle. Feynman said it, and he's right. And one thing that I told you yesterday when I began, there are very few solvable models that you have been learning throughout your studies, including Kepler problem, harmonic oscillator, and so on. In fact, it can be shown using these abstract techniques that all in all, any, with probability 1, or any exact solution that you know about is related to the Bethe Ansatz. Directly or indirectly, there is some Bethe Ansatz thing hiding into it. So now I'm going to teach you the Bethe Ansatz for the exclusion process. And very fortunately, I think it's the simplest example to learn the Bethe Ansatz. In fact, it's perfectly equivalent to the spin chain that Bethe studied in '31. But you don't have to go into the complicacy of Pauli matrices, quantum mechanics. There's nothing quantum in it, and it works the same. And I think it's the best tool, best model to learn about the Bethe Ansatz. So let's do it now. take it as an example to learn the coordinate Bethe Ansatz. We study the exclusion process on a ring of L sides. It's a periodic ring. You have particles and holes. Particles can jump with rate p in the positive direction and with rate q in the negative direction only when it's possible and you don't have double occupancy. Okay? So configuration of the system is given by the location of the particles, and I have L sides and particles, and I will just say that particle number 1 is on site x1, particle number 2, so configuration is given by the location of the n particles, locations. Okay? And the probability of evolution, the probability of a configuration at time t, I can write it as pt of x1, xn. It satisfies the master equation. Okay, so I just write this master equation. So here one has to be a bit careful. So I just write it crudely first, and then you'll. Okay, will you allow me a change of notation which is not completely kosher? Instead of P, it's the same thing. Let's write it psi, just to emphasize the analogy with quantum mechanics. It's not really important. So how can you enter this configuration? Maybe a particle which was one side behind somewhere jumped by 1 with probability p. So the ith particle was located at xi minus 1 and it jumped by 1. All the others stayed at the same place. Or a particle that was at xi plus 1 jumped. I will complete the equation later. From xi plus 1, it jumped back. All the other ones are the same. And this is xi minus 1. And of course, you can leave this configuration. So you can leave this configuration if any particle jumps forward with probability p, or jumps backward with probability q. So this seems to be the Markov equation of the system. Is it true? Did I do some mistake? Do you agree that this is the Markov equation or it's not? Well, one has to be careful. One has to be careful because there may be some non-authorized jumps. Okay? If two particles are sitting next to each other, for example, if the position of the particle xi minus 1, the particle I minus 1 is just behind the particle xi, I cannot jump backwards. Okay? So one has to be careful. So here the sums, there is no good way of writing it. So again, you have to work it through and find your own understanding or your own way. There is no good way. This is just a marking to say that be careful. The sums are restricted. So these are not all possible sums. Sums are restricted to indexes such that xi minus 1 is less than xi minus 1 or xi plus 1 or xj. Let's call it j here. It's easier. Xj plus 1. It's a dummy variable, but maybe it's more pedagogical to change the name. Xj plus 1 is bigger, is less, of course, than xj plus 1. This tells you that the jump forward is allowed because there is enough space. The site next to the jth particle is empty. because the j plus 1 particle is far away. And this tells you that the jump backwards is allowed because the site behind the ith particle is further back. The I minus 1th particle is further back than the site I minus 1. Okay, this looks a bit awful, I'm sorry, but I think there is no. You remember this one? This is just the same thing, but written in precise coordinates. So a configuration is defined, that's an important question. Thank you for asking. A configuration is defined by the position, the location of the particles. So I just, if I know where they are, I know that the other ones are empty. Okay? So x index I minus 1, this is the location of the I minus 1th particle. Okay? And this is the location of the ith particle. So this tells you that the I minus 1th particle is separated from the ith particle by more than 1. It's more than 1 apart from it. Okay? This tells you that xi minus 1, this is the I minus 1th particle, this is the ith particle, and the distance is more than 1, so there is one empty site between them. And this tells you that there is one empty site between the gth particle and the g plus 1th particle. This is an index. I mean, I perfectly agree that these things are not simple. They are not extremely difficult, it's just heavy. But you cannot make it, I don't think you can make it lighter. Okay. Yes? Where? I made a mistake somewhere? Oh, yeah, of course. Yeah. Of course, sorry. Yeah, there are two terms. Okay, so now this is the Markov matrix. I agree. I mean, the first time I saw it, I found it hard to digest it, but okay, I mean, sorry, it's like that. That's life. And life is tough. C'est la vie, as we say in France. But okay, and we have to solve this equation. And this is a linear equation in psi. So one good way to solve it is, before solving it, is to diagonalize it. So I want to find the eigenmodes. I want to find the eigenvectors and the eigenvalues of this linear equation. The location of the I minus 1th particle and the ith particle differ by at least 1. I can put the plus 1 here if you wish. It's the same thing. So this is the location of the ith particle, this is the location of the I minus 1 particle, and they are more than 1 apart. If they are more than 1 apart, it means that there is a hole, at least one hole in between, and jumps are allowed. Is it okay? I think the best way is to do it by yourself. Okay? Sorry? You're right, yeah. It will be longer to write, and it will not feel set into one equation in one line. No, you're right. You can put theta functions if you wish. You can put thetas of xi plus 1, or xi less than xi plus 1, minus 1, or things like that. You can put thetas instead of primes. Again, there is not a unique method. I'm not sure there is a best method. You have to try it for yourself and get convinced. Okay, I think we spent a lot of time on this master equation, and we want to diagonalize it. We want to find the eigenmodes. So now starts the Bethe Ansatz. Sorry, I just don't hear anything. Yes. No, because you see, P increases the position. So if the ith particle were located on xi minus 1, then by jumping by one site forward, it will reach the site xi and reach my configuration. If you look, where are you? If you look at this particle, to enter this configuration, you could have started from the particle here. What is the label of this site? This is the site xi minus 1, and you jump with P forward to this site. Is it okay? Yeah? Okay, so this was the easy stuff. Now we start the complicated thing. So again, Perron-Frobenius tells us that there is only one zero eigenvalue, the stationary state. The matrix method takes care of it. Well, in the periodic case, you don't even need that. The flat measure is invariant, as I told you yesterday. But we want to know the excited states. We want to know the eigenvalues of this matrix. And you see, in this model, n is conserved. Of course, there is no destruction or creation of particles. So we shall do it exactly as Bethe did it. We shall try to see what happens for n equal to 1, n equal to 2, n equal to 3, and try to understand. So we shall first solve the problem with only one particle. So this is very easy. You all did it in solid state physics. This is just, I don't even know the name. One electron in a chain. So this is very easy, but the only difference here is asymmetric. But if we do it, we can write it again, and this is simpler. In the case of only one particle, n equal to 1, the eigenequation, so there's only one, so I don't call it x1, there's no need because there's no x2. I call it x, and my equation, my general equation, becomes p x I minus 1 plus q psi xi plus 1 minus p plus q psi x. So this is a very simple equation to solve. Of course, I'm on a ring, so psi is periodic. So this, I will not enter into the details. You solve it your favorite way. You can say that it's just a recursion relation, a second order recursion relation. And you know that the solutions are given by plane waves. So psi of x will be given by two plane waves, a z plus to the power x plus b z minus to the power x, and z solve the equations q z squared minus p plus q minus e plus p plus q z plus 1 plus p, sorry, is equal to 0. So this is quite easy. But of course you have periodicity, so you must have z to the power l equal to 1 because of periodic boundary conditions. So this fixes you that, in fact, you must have plane wave. And in fact, it kills one of the two z's, and the solution is really given by psi is an amplitude times z to the power x with z to the power l equal to, such that z to the power l equal to 1. Okay, I mean all this you know perfectly. And what is the energy? The energy is given by, you just substitute. So it's pz, p over z, plus qz minus p plus q. I mean, I'm sure that all of you solve the case p equal to q equal to 1, just a tight binding model, or I don't know, there are 36 names over that, or okay, any name you like, but you already did it. Okay, no question? I mean, this you can do, or just look in Kittel's book or any book in solid states. Okay, now let's go to the to n equal to 2. I need another blackboard. N equal to 2. I have two particles located at x1 and x2, and I can choose that x1 is less than x2. So if I draw my little circle, I wish I was much taller. No, it's not easy. Maybe I should buy a small a piri, as we say. I don't know the word in English. Something, a small stool. So I could write the better equations up there. Okay, never mind. And the general equation that I just obtained from this one is given by. So when is this equation going to be valid without any problems? When x1 and x2 are separated. This is going to be cool, no problem. Suppose that x1 minus x2 are more than 1 apart. So there is a hole in between, so no restriction. Everybody can jump backward, forward, whatever you like. So now I have no philosophical problems. I can just write everything. So x1 can jump backwards. X2 can jump backwards. X2 minus 1. They can jump they jump forward, sorry. They can jump backward. Can you read me? Yes? If you want me to write bigger, I can. Not higher, but bigger I can. Okay. And then you have the last terms. So minus 2p plus q psi of x1, x2. Okay. And this is really the case where I have no problems. The particles are far apart. They are separated by, okay, I'm not drawing the ring. They're just separated by more than one side. So this is for x1 minus x2, bigger than 1. Okay? So this is the generic case, the general case. This is generic. Now I have the special unpleasant case where they sit next to each other. Because if they sit next to each other, the one which is backward cannot jump forward, the one which is forward cannot jump backward. So I have to be careful. This is exactly what the prime tells me here. So let's be careful and use a different color. So this is a special case where they are next to each other. So let's call it the adjacency case. So they are next to each other, x1, x2, they are here and here. So this is the case where x2 is the next site, is located at the next site. The two particles are next to each other, they are neighbors. This is the first particle, this is the second particle, this is x1, this is x2, but unfortunately x2 is x1 plus 1. So here I have to be very careful, and my generic equation is not valid anymore. I have to take into account the prime, and the equation becomes psi of x1. So x2 is x1 plus 1, so let's write it what it is. So x1 can go backwards. I mean, no, x1 can come from backwards. It can come from this configuration. Okay. x2 can come from a configuration where it was here. So x2 plus 1, which is x1 plus 2. That's all. And the last terms are either this one goes backwards or this one goes forward. So it's minus p plus q psi of x1 plus 1. Do you agree with me? This is a special case where they sit next to each other. Can you read the blue? No? Oh, you should have told me. Okay. No, because this is important. Well, yeah, blue is scattered. That's why the sky is blue. No, it's not fun, it's true. Now this is important, so I don't know how I can do that. I will erase it and write it again. 1 plus q psi of x (1 plus 1 x1 plus 2 minus p plus q psi. We don't need that today anymore. x1 plus 1. Okay? So what we have to solve is this set of equations when x1 and x2 are far apart, separated by one hole at least. We have the general case, and then we have the special case when x1 and x2 are next to each other. But of course, we cannot forget about it. The set of equations is really this set of equations. Here? Yes. Thank you. Yeah. Okay. So now comes the different steps of the Bethe Ansatz. In fact, if you understand the n equal to 2 case, you get most of it. So you see this equation is not the same as the general equation because there are some terms which are missing. So there are two ways of trying to solve this. You can say, okay, I solve this equation when this condition is true, and I solve this equation when this condition is true. But this is very awkward. Okay, this is complicated. So one way, which is perfectly equivalent, is to say, okay, I solve this equation everywhere, and here, this equation is almost this one, but there are some missing terms. Okay, so we can write the missing terms. We can write them in red. So what are the missing terms? If this generic equation were valid for any values of x1 and x2, including x2 is equal to x1 plus 1, we would get these terms, but we would get some extra terms. So these extra terms, if I just write and copy just blindly, just by substituting x2 is x1 plus 1, I will see that in fact there are 6 terms here, only 3. So there will be 3 missing terms, which are, unfortunately, which are not there. And there are these 3 terms, plus q psi of x1 plus 1, x1 plus 1, minus p plus q psi x1 plus 1. If it is not the case, my equation was like that, it would be the same equation as in the generic case, unless I did a mistake in writing, but it should be. Do you agree? Yes? Unfortunately, it's not the case. I mean, these terms are not there. So the little trick, which is not a huge trick, this is not the main trick of the Bethe Ansatz, is the first trick, is to say, okay, another way of saying it, I just solve this thing everywhere, and I put this equal to 0. So instead of having a special equation, I have a boundary condition. So So I just forget about my special equation, but I put this boundary condition, and I remove that. It's the same thing, okay? Instead of having one generic equation and one special equation, I implement the generic equation absolutely everywhere, and the missing terms, I just cancel them. So it's a cancellation condition. So this was the first observation of Bethe. I don't know how many else, but you will correct it. Cancellation condition. Okay? So you replace the special equation by a boundary condition, kind of. If you go to the continuous limit, you see it will give you a kind of Dirichlet or Neumann boundary condition. And now, you try to solve it. Because you know, these kind of equations, I should have said it before, you're familiar with them. These are really hopping equations in a lattice, like electrons in a lattice. Okay, it's asymmetric, but it's not a big deal. So you know that kind of plane waves are going to solve this. So if I'm a bit blind or bold, I would say that my generic equation, well, I've learned in books, in solid state physics, my generic equation is solved by plane waves. So I can write a priori psi of x1, x2 as exponential I k1 x1 times exponential I k2 x2, but usually people don't write it like that, but it's perfectly equivalent. I can write it as two plane waves, z1 x1, z2 x2. Okay, usually we like to write z1 is a k1, z2 a k2, but here, okay, the notation is like that. So forget about the wave numbers. And then what is the energy going to be? Oh, great, I have plenty of colors. I love that. Thank you. As usual, it's the cos theta, cos k, but because of p and q, it's slightly different. So it's going to p times 1 z1 is missing. So 1 over z1 plus 1 over z2. And I don't need the sum. Plus q z1 plus z2 minus 2 p plus q. You agree with that? This should be simple. You just substitute and you get the energy. Okay? But of course, this is not the whole thing. Otherwise, it would be trivial. Well, then you say, okay, I found the solution of this generic equation, and I just want to implement my cancellation condition. So you just say, okay, I will try to calculate the value of the amplitude so that the cancellation condition is okay. Well, it will not work. First of all, this equation is linear, so the amplitude will just be washed away. You can just factorize it, and it's a non-zero amplitude. And now if you just substitute, you will see that it will give you a relation between z1 and z2, which has no reason to be valid in general. So this I don't do it. It's a simple exercise. Just substitute the general solution here of the generic equation into this equation, and you will see that it blocks. It doesn't work. It may seem to you that it will work in the beginning, but if you go further, you will see, for example, that you cannot implement the periodicity condition, things like that. So it's blocked. Okay? We can talk about this special thing later if you wish, but believe me, it's very simple to check. So now we are stuck. Okay? And now comes, well, the genius of Bethe, the absolutely crucial observation. So now comes really the Bethe Ansatz, crucial observation. We are looking for eigenvalues of this equation with eigenvalue E, eigenvectors and eigenvalues. Okay? And you can observe here that the eigenvalue E is symmetric with respect to Z1 and Z2. If I exchange Z1 and Z2, I have the same formula. Yes? So there is another plane wave which gives rise to the same eigenvalue, which is just a plane wave obtained by permuting Z1 and Z2. So if I take another plane wave, there's a twofold degeneracy, if you wish. If I add, not in blue, maybe yellow, it will be visible. If I can extract it. Okay. If I add another plane wave, B, amplitude, Z2 to the power x1 and Z1 to the power x2, can you see it? This thing has the same eigenvalue. You just substitute. So this is still an eigenvector with the same eigenvalue because of the degeneracy of the generic equation of the tight binding model, if you wish. Cos k, cos minus k, if you wish. And then now I have two terms. So more freedom. Especially I have the ratio of the amplitudes, which will not cancel away in this linear equation. And now I can choose A and B, or more precisely, the ratio of A and B, so that the cancellation equation is satisfied. So this we can do immediately. If you just substitute this form here, you will get a condition on A and B. So if you allow me, I will not call them A and B, just for further discussion tomorrow. I shall call this A12, and this one, instead of calling it B, I call it A21. It's just a change of notation. I substitute it here, and I get one equation for A12 and A21, just putting it back and saying that it's true for any x1. I get one condition. I get that A21 divided by A12 is given by minus Q Z1 Z2 minus P plus Q Z2 plus P divided by Q Z1 Z2 minus P plus Q Z1 plus P. Okay? And now, can I take 5 minutes more? I will finish the n equal to 2 case. Now, the eigen equation is satisfied in the generic case together with the cancellation equation. So we have found a solution of the whole eigen equation for all values of x1 and x2, including the special agents neighboring case. Okay? So one thing. So no, this condition, how can I say? The special case implies this condition on the amplitudes A1 and A2, or A12 and A21. Okay? This form is a solution of the generic equation, but now I can choose these two guys. If I choose them like that, my cancellation condition is satisfied. Before, in the naive case, I had only one, and I had no choice. I was just blocked. Now I have two, so I can play with the relative amplitude of the two plane waves, and by playing on the relative amplitudes like that, I can satisfy the cancellation condition. Okay? And I know the eigenvalue, which is given by that. So in fact, we have diagonalized the exclusion process on a ring for the two-particle case completely. But of course, it's not completely finished. We are on a ring. There are boundary conditions. There is a periodic boundary conditions. This is slightly tricky. What should I remove? I will remove this equation, if you agree. It will pop out tomorrow again in the general case. So we have to impose periodicity. And here we have to be slightly careful, because periodicity does not mean that if you add L to x1 and x2, you will end up at the same place. Of course it means that, but it's not enough. There is a kind of twist. You see, this is also a slightly difficult thing. Naively, you would say, okay, it's periodic, so psi of x1 plus L, x2 plus L is psi of x1, x2, because it's L periodic. Okay, this is true, but this is not enough. There is something more subtle than that. The thing is that it's on a ring, and you have your two particles. Your particle x1 here, and your particle 2 here, site L here and site 1 here. So here again, you have to believe me, these kind of things come with habit. So the phase space that of the problem is indeed this one. We decide that particle x1 is behind particle x2, and both are between 1 and L. But something bizarre could happen. This particle x2 could jump, pass through L, and come behind x1, and become the lagging behind particle. So you have to take this into account, and the idea is that, in fact, if you have x1 and particle x2 comes at L plus 1, this should be the same thing as particle 2 becoming particle located at 1, and particle x1 becoming the second particle. So this is slightly difficult, but it's true. More generally, if you have x1, x2 plus L, so somehow x2 has gone beyond one term, then x2 becomes x1. The second particle becomes the first one, because it has gone here, 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 and you have to swap the coordinates. So this is okay. This is again slightly unnatural, but this is a right boundary condition. Again, this is something which comes with habit, but it's really the right boundary condition. Okay. So now I think I can almost get the better equations. Now we substitute in this equation, we substitute the general form. Okay, I wrote it the other way in my paper. Well, yeah. This one? This tells you that I have my particle x1, I have my particle x2. Okay? x2 is in front of it, and it's between 1 and L. Now suppose x2 is moving, and crossing L. Okay? Then x2 will become the particle which is behind, because this is a positive direction, anti-clockwise. So x2 now we have to relabel it by x1. That's what this equation says. Okay? Or this one if you wish. This one is equivalent, it's simpler. If particle x2 comes at site L plus 1, it is in fact the same thing as having a particle at 1 and at x1. Yes? So now I take this equation, for example this one, and I take my general form, which is here, and I just substitute. So just do it. I was going to do it, but I'm getting late. And you will find that, in fact, you find another relation. This is just a simple exercise. You just substitute and say that this is valid for any value of x1. Okay? And you get this relation. You get two relations. It's a pure substitution. There's nothing more than that. Okay? If you wish, we can do it tomorrow, or we'll do it tomorrow in the general case. So now you have these two equations. This was fixed by the cancellation condition. This is fixed by the periodicity. Of course, I can eliminate this ratio. And I will get two equations, one for Z1 and one for Z2. So these two equations, I shall write them down here. So it's Z1 to the power L is equal to minus Q Z1 Z2 minus P plus Q. I'm just putting it back here. Z1 plus P divided by Q Z1 Z2 minus P plus Q Z2 plus P. And I have the same equation just by exchanging 1 and 2. So if I exchange 1 and 2 here, I have the other equation for Z2 to the power L. Okay? So this is a quantification condition for the momenta Z1 and Z2, the plane wave, the wave numbers. So it's a quantification condition. And these two equations, these two coupled equations, so there are two of them. There's one for Z1 and one for Z2, same type. They are called the Bethe Ansatz, the Bethe equations. And they are, in fact, the result of the Bethe Ansatz. So what have we achieved? What have we achieved? We started with a system with two particles. And if you look at it, the phase space is of dimension L square, L minus 1 over 2. These are the two possible positions of the two particles. So I have a big matrix of size L square, L minus 1 over 2. Okay? So if I want to diagonalize it, I should solve the characteristic polynomial, which is of degree L square, which means that if I take a system of size 10, L minus 1 over 2, but it's of order L square. If I take a system of order 10, I will have a characteristic polynomial which is of degree 45, 10 per 9 divided by 2. Okay? It's huge. It's quite big. If I take a system of size 50, it will be huge. Okay? It will be something like 1000, the degree. But what Bethe tells us is that the solution, the eigenvectors, are of the form of plane waves. The amplitude of the plane waves are fixed by the values of the wave numbers, if I know Z1 and Z2. And Z1 and Z2, which are the wave numbers which give you the form of the plane wave and also the eigenvalue, the energy of the system, Z1 and Z2, they are obtained as solutions of two polynomial equations, two rational equations. So you'll tell me, okay, but what have I won? I had a characteristic polynomial, and I still have two polynomial equations. But here, the degree is L, not L squared. Okay? It means that if I have a system of size 10, I have to solve two polynomials coupled, okay, but of degree 10. If I have a system of size 50, I don't have to solve a characteristic polynomial of degree 1000, but only of degree 50. And this is, in fact, the equations may look awful, but they are infinitely simpler. They are extremely symmetric, and we shall, in fact, solve them in this course. I'll teach you how to play with these equations. These equations are infinitely simpler than just plugging in the characteristic equation of the Markov matrix. If we had three particles, the Markov matrix size would be of order L cube, L minus 1, L minus 2 over 6. Here, we shall still have equations of degree L. If we had a half-filled system, the size of the Markov matrix would be of the order 2 to the power L. So if a system of size 10, the characteristic polynomial would be of the order of 1000, the degree, okay, degree of 1000. Here, we are still having equations of degree, the size of the system, and not exponential of the size of the system. So this is although it looks a bit bizarre and a bit complicated, this is just a huge simplification of the model. And in fact, this tells you that the model is computable. You go from exponential complexity to linear complexity. This tells you that this is computable, and indeed Mathematica can solve systems of size 100, whereas the Markov matrix is of size 2 to the power 100, which is something infinitely big, which is beyond any computer. But these equations can be solved for a system of size 100. But what makes the beauty of these equations is that they're extremely symmetric, they're extremely pretty, and you can really do some analytical progress with them. And this is what we are going to learn in the next lectures. But next lecture, maybe we shall talk maybe later and you'll tell me what you wish. The Bethe Ansatz doesn't stop here. I showed you for n equal to 2. At n equal to 3, there is a miracle which happens, which is the key to the solvability of the problem. So I'm going to tell you that tomorrow.